Okay. We will tell us about some problems, statistical physics.
Yes. Thanks, Sammy, and thank everyone for coming under this weather. And today I would like to talk about reconstruction of trees and hypertrees. And this work, and actually the second part is joint work with Princeton student Ardea Pandey and my advisor Yuri Poliansky. And the first part is about classical theory. And let me first introduce the Gaussian trees model. In this model, we start with a rooted infinite tree. And here we have a two regular tree. That is, every node have two children. We can consider irregular trees or other tree structures. And there is a signal on the root, and the signal propagates downward the tree. So suppose the signal at the root, we choose it uniformly random from plus minus. And on every edge, suppose the parent is U, the child is V, then the signal at V is follows this distribution. As sigma of V is equal to sigma of U with probability 1 minus delta, and with is equal to negative of sigma U with probability delta. That is to say that on every edge, you flip the bit of the parent with probability delta. And in this way, we assign a signal at every node of the tree. Let me mention that it's easy to generalize this to higher alphabet, but in this talk, I will mostly focus on the binary alphabet case. We will generalize it in the second part, but not to higher alphabet. Okay, so what is the question for this model? It's about this reconstruction problem. There are many equivalent ways of formalizing this question, but in human language, it says that we will observe signals deep inside the tree. For example, signals at vertices with in level D of the tree, and we want to reconstruct sigma rho. That is, given these observations, we want to emit a guess about the root signal. And of course, it's not possible to exactly determine sigma rho. So we want to win with non-trivial probability, with a probability larger than half plus epsilon, where this epsilon should not depend on k. Equivalently, we can consider two distributions. The first distribution is sigma Lk conditioned on the root being plus, and another distribution, and also consider other distribution where is the sigma Lk conditioned on the root being minus, and take the total variation distance between the two distributions. And we say, okay, we say this is possible if and only if this goes to larger, goes to some positive value as k goes to infinity. Equivalently, we can write this using neutron formation, which says that the mutual information between the root and the leaves goes to some positive value as k goes to infinity. So this model has several parameters, that is the structure of the tree and this delta. And the question is, for which parameters reconstruction is possible, and for which parameters reconstruction is impossible. So this is the definition of the problem.
Is delta the degree of the tree?
No, the delta is some parameter.
It's small.
That is a noise. The noise on every
So is the degree also a parameter?
We can consider arbitrary tree structures, but if we consider regular trees, then we can say deregular tree, and then D will be a parameter.
Just to clarify, delta is a half, you cannot, and the hope is for smaller delta, you can do something.
Yes. And before talking about the results, let me give you some reasons why this is an interesting problem. And actually, I'll give you 4 reasons. And in the order from more abstract, more theoretic to more concrete, more practical. Okay, the first one is that this problem is actually a fundamental problem in probability. There are some other ways we can rewrite this reconstruction problem. And there will be some words that you might not be familiar with, but that's fine. This reconstruction is possible is equivalent to saying that the free boundary Gibbs measure is non-extremal. Which is also equivalent to saying that the this free boundary Gibbs measure is not tail trivial. And this last statement have some relationship with some very basic results in probability. That is, in Kolmogorov 0-1 law, is a very basic statement in probability, which says that if you have a sequence of IID variables, independent variables, then the tail sigma field of this sequence will be trivial. This can be generalized to Markov chains, such as let's say Z-index Markov chains.
Can you say the statement is your version of Kolmogorov 0-1 law about tail trivial because it may clarify what tail trivial is?
Yeah, I don't really want to.
You don't want to do it.
Yeah.
Okay.
Because it needs some probability jargon and it's not that easy to digest. Okay, it's basically it says that if you have some event that only depends on the anyway, let me do it. Okay, suppose we have a sequence of variables, infinite sequence, and we can consider the sigma field generate a sigma field of the tail variables, which means that events that you can like evaluate for this set of variables, and the tail field is the intersection as n goes to infinity of the of these sigma fields, which says that which are events you can evaluate by considering any tail of this sequence. And the tail trivial means that for any event in this field, it either happens with probability 0 or happens with probability 1. And in Kolmogov's version, this infinite sequence of variables are IID. And one generalization is to consider where this is a Markov chain that is each xi plus 1 is achieved from xi by applying some Markov kernel. And classical results shows that, for example, if your Markov chain is ergodic, then it has trivial tail. And from here, you can consider like generalizations of this Z-index Markov chain theory. And one of the more popular generation is on more higher dimension lattices. And it's like a major problem in probability. And in here we are not doing this high dimensional lattices, but we are doing tree index Markov chains. Well, because the chain, it can be considered as like a degenerate version of the broadcasting on tree problem. So
well, it can also be if you consider the full distribution on level K, then it is a Markov process, right? For level K minus 1.
Yes, that is true. Here I want to emphasize that with the tree index Markov chain, like the state space at every vertex is the same. Therefore, so this problem about tail triviality of certain Gibbs measures can be seen as like a vast generalization of Kolmogov's 0-1 law. And at this point, I would like to, before talking about the other three motivations, I would like to talk about known results about this model. To here. So so this particular problem about the tail triviality of the free boundary base measure or reconstruction on trees is first studied by Spitzer in 75. Yes, 75, and he claimed that it is always extreme. And okay, but it is soon found that this is actually not true. I should say that he studied a lot of problems on this free boundary Gibbs measure, and he proved a lot of things. But this particular statement is unfortunately incorrect.
But the claim was being extreme means that it's always reconstructible.
It being extreme means it is always not reconstructible.
For any delta.
Yes.
For any positive delta.
Yeah. But it's 2 years later, it was found out that this is actually not true. And
can you write a little bigger just for
sorry.
the Zoom audience? Yeah, from now on. Yeah.
Okay. It's provides no extremal if d times 2 delta square is larger than 1. And d is the number of children of every node in the tree. For example, we consider d-regular trees. And this result was put into context of a previous result that's more and still in 78. We found that this result actually is implied by previous result of Testing and Stiegler in 66. Testing and Stiegler studied multi-type Galton-Watson processes and proved a number of fundamental results. And they found that their results on multi-type Galton-Watson processes actually imply non-extremality for d times 1 minus 2 delta squared larger than 1. And so we have this non-extremal part, but what is the threshold? This is about 20 years later. Left, right, and Zagreb in 95. They prove that this is extremal if and only if d times 1 minus 2 delta square is less than or equal to 1. And another result I want to mention is by Evans, Penyang, Harris, Roman, around the same time, and like they had a result around the same time, but that proved the same result for general trees.
Well, D is the average degree. What is general trees?
General trees means not necessarily regular tree.
So the D would be the average.
D will be replaced by what's called a branching number, and it is often the same as average degree, but not always. Okay, so that's the history of this problem, and the second motivation is from statistical physics, and actually also from statistical computer science about random constraint satisfaction problems. So suppose we consider random some CSP such as a random category or random K-set.
Bigger.
The physicists have some very good and very precise predictions about the geometry of the solutions of these CSPs. So from left to right, this is as D increases. So we consider a random graph and let the class density increase. When this shows the geometry of solutions.
So D here is the number of constraints that a variable participates in.
Yeah, it could be. Yeah.
Yeah, in coloring it is exactly the same. The degree is the number of constraints that the variable participates.
Right.
When D is very small, all the solutions will be in a single cluster. And when D goes slightly larger,
Think about the neighborhood structure. You look at timing distance.
yeah, there are some several different ways to define this neighborhood, but most of them are equivalent. Get you the same result. For example, you can say two solutions are in neighbors if their Hamming distance is little over n.
Yeah, but anyway, you have to define a metric before you say connected.
Yes.
Yeah.
as your D goes slightly larger, it goes through something called clustering phase transition. Or clustering.
So we think of B increases, but the number of colors is fixed.
Yes.
So when this much below the number of colors, right, when the degree is much smaller than the number of colors, there's no problem. Colors, right?
Yeah.
It's very fun.
It goes through a phase transition called clustering, where instead of one big cluster, you have exponentially many clusters. And these exponentially many clusters have almost the same size. And the clustering phase transition is conjectured to be the threshold at which local Markov chain algorithms fail for sampling these distributions. For example, you could consider Galois dynamics, which is a local MCMC algorithm, and it is predicted to fail at the clustering threshold.
The cluster will still be exponentially large, but there'll be,
Yes.
right? They are
Yes.
still exponentially large, but there'll be exponentially many of them.
Yes. And as your D goes larger, you go through another phase transition called condensation. And at the condensation phase transition, you instead of exponentially many clusters, you now have like the clusters. You have like the cluster sizes decay exponentially, and you have a constant number of clusters that occupy a constant fraction of all the solutions. And the last is the satisfiability phase transition, where you don't have any solutions. So these are the predicted phase.
Sorry, what is the random coloring here?
Random coloring here, we mean that we choose a addition in random graph and then consider the number of Q colorings, number of proper Q colorings of the this random graph. You could also consider regular random graph, but yeah. These are the predicted phase transitions for this random CSPs. What's the relationship with broadcasting trees? The claim is that the conjecture is that the broadcasting tree, the reconstruction threshold, has a close relationship with both clustering and condensation. So the conjecture is that the reconstruction threshold is actually the same as the clustering threshold. And
what are the relative parameters? What, here you have Q and D, there you have delta and G and other.
Yeah, to state this relationship, we need to consider the higher alphabet version of this model. For example, for coloring, we'll have the labels will be from 1 to Q, and on each edge is the channel will be, you go to a uniform random color that is not same as the input.
So the structure, that problem is on trees and this problem is on erosionary graphs, and somehow there is still a conjecture there is a relationship.
Yes. Yeah.
You sort of emulate, I think, that the connection, you emulate the global dynamics on your graph.
I see. And you're locally tree-like.
If you evolve it and the graph was a tree.
I see.
Like it's a random graph in the beginning.
So locally,
locally. Yeah.
So I don't know if this is like precise, but as Abby said, like you're looking at the random graph and locally, like it looks tree-like.
Yes.
And the connection, what it's supposed to be that like you want to say that like after a certain distance, either the colors could behave randomly or have some connection to the color of a certain vertex. Like what is What's going on here?
Yeah, the question is whether in this process you have long-term correlations or not, and it depends on the problem. I mean, some problems do and some problems don't, and some problems this global dynamics does produce random or almost random coloring or assignment, and in others it doesn't. And this what depends on the threshold. Sometimes it's provable, sometimes it's conjecture.
This is same as correlation decay, like.
It's related to correlation. This is this broadcasting problem is exactly about correlation decay of what happens far away from where it started. Yeah.
And okay, so for the condensation threshold, there are like more proved results. So Gotcha outline first Perkins and Gabarova in meeting. They prove that the condensation threshold. Okay, they prove that for certain models, including the random coloring, but not clear if it includes the k-set. The condensation threshold is the threshold at which the threshold at which there is a belief propagation fixed point with positive energy. And this BP fixed point is something that is something that is closely related to the broadcasting on tree model. And we will see what is the BP propagation later. I will not define it now. And energy is some functional on this BP fixed point.
The beta free energy.
Yes. And this clustering is the threshold at which there is a non-trivial fixed point. And trivial fixed point always have zero free energy. So this studying this broadcasting on tree problem will give you the conjectural clustering threshold and give you a lower bound on the compensation threshold. And in some cases, these two thresholds will match.
Is the second one also a conjecture, or is the second one actually?
Okay, this is approved for some models. And interesting I want to say about this result is that they determine the condensation threshold for a large number of models in terms of this BP fixed point. However, evaluating this condensation threshold is actually non-trivial, and it still requires studying very closely of the rebroadcasting on tree model to actually evaluate this threshold. And in some cases, there are conjectures of the exact threshold, but they are not proven. And the third motivation is come from community detection. Community detection is about finding communities in complex networks. In real life, there are many different kinds of complex networks such as friendship network or some power grids, things like that. And they share some properties such as they have some communities, means they have a set of vertices where the edge density inside the set is much larger than the average edge density in the whole network. And the theoretical study of this community detection question went popular about 10 years ago by Discrete et al. And they considered what's called stochastic block model. And in this, it's a random graph model where you have n vertices and you give them random labels that is IID from uniform plus minus. And now you construct a random graph. Where for every vertex, every pair of vertices u and v, you add this edge with probability depending on whether the two endpoints have the same label. That is, it's an edge with probability a over n if xu is equal to xv, and with probability b over n if xu is not equal to xv.
A is greater than B.
We could consider arbitrary A and B.
Okay, but it would be, these would be communities if A.
Right, yes.
And otherwise there'd be.
Yes.
Right, each other like that.
Yeah, for practical considerations, A is larger than B. And with the theorists can consider arbitrary A and B. And actually, the case A smaller than B is not, is actually quite useful in theory because they naturally correspond to a random coloring or random cases. And the question the question is called the question for stochastic block model is called weak recovery, where you want some given the graph G, you want to put reconstruct the labels. You want to estimate x hat such that the distance between x hat and x is less than trivial.
What is distance field? This is a.
Yeah, okay. So the distance here is the minimum of the Hamming distance between x hat x and the Hamming distance of negative x hat and x. This is because you cannot reconstruct, you can only reconstruct up to a global sign flip.
In the case of two communities, I guess.
Yeah, when you have more symmetric communities, you need to consider like the symmetry group.
Yeah.
And for this one, the weak recovery threshold is established 10 years ago. It's by Masuli in 14 for the positive side, and by Mosso, Niemann, Slide, 15 for both the positive part and the negative part. They established that weak recovery is possible if only if A minus B squared over 2A plus B is larger than 1. And so what's the relationship between this and the reconstruction trees? So if we consider this random graph, we consider a local neighborhood of a vertex, then the local neighborhood structure together with the labels will have the same distribution as the broadcasting trees. So this corresponds to the broadcasting tree model where the average degree is a plus b over 2, and the delta is equal to b over a plus b. And if you do some algebra, you can see that this quantity, this threshold, is equal to d times 1 minus 2 delta squared. So in this case, the reconstruction threshold is exactly the weak recovery threshold. And more generally, if we consider more communities, then the relationship is that reconstruction is impossible, will imply weak recovery is impossible. This reduction is proved in Mossoni-Mann's slide. And if you are above the Statistical threshold, which is d times 1 minus 2 delta squared in the binary case, then weak recovery is possible. For the binary case we talk about, the reconstruction threshold is the same as the Statistical threshold, which are both d times 1 minus 2 delta squared. But for more general models, this d times 1 minus 2 delta squared has a natural generalization, which is d times lambda squared, where lambda is the second largest eigenvalue of the broadcasting matrix. And that threshold is called the Statistical threshold. And in general, these two reconstruction threshold and Statistical threshold will not be the same. But
a question. So, do you consider efficient reconstruction, or you just consider if like you can reconstruct it?
Yeah, that's a good question. So for efficient construction, okay, for this result, the positive part is efficient reconstruction. It is there's an algorithm by analyzing by computing the eigenvectors of the certain certain non-backtracking walk matrix of the graph, and that algorithm is polynomial time, and I'm not quite sure if it's linear, but it's quite efficient. And if in general, it is proved that this method will work above the Statistical threshold. That is, when you are above KS, you have an efficient reconstruction algorithm. And the conjecture is that below KS, you do not have the efficient reconstruction algorithm. So, the weak recovery threshold we are talking about is like the informational threshold, and there's a computational threshold, and it's conjectured that there's a gap between the informational threshold and the computational threshold, and this is called the information computation gap. It is
usually like between the clustering and the condensation. You believe, right, that they correspond, clustering and
Yes.
and the condensation.
Yes.
You can still do efficiently the before condensation, then after condensation information theoretically is possible, but not efficient.
Mm-hmm.
Wait, but isn't that like cluster threshold? Like, do you mean like even like below this threshold, one can have some efficient algorithm for recovering? Or it's impossible?
Below the reconstruction threshold, it is information theoretically impossible.
Okay, I see.
And you have above that, above reconstruction, it is like information theoretically possible. But the question is there an efficient algorithm to do that? And And the conjecture is that the threshold for existence of efficient algorithm is at the Cassin-Stevens threshold, which is above the reconstruction threshold.
So in terms of your application too, is this threshold, which one does it correspond to in this case?
Yeah, so if you define things correctly, then the weaker coverage threshold for stochastic Born model is the condensation threshold here. Yes. Yeah.
I just wanted to clarify something here, like this picture is for a problem that doesn't have like a planted solution, right? Like here.
No, there's no
like
planted
one
solution.
single planted solution. So I'm not sure, like, yeah, what does clustering or condensation mean? If you have just one planted solution, right? This is a problem.
They are like two different models, but you can like below the condensation threshold, these two models will be mutual contiguous, and so will have the same behavior. And above that, they'll be different. And the fourth motivation is I won't be talk too much about it, but it's very amusing. Let me explain this. So in May of 2023, that's last year, there was a workshop at Harvard on graphical models, and Alkaner Mossel gave a very interesting argument that the broadcasting on tree model is actually a very nice model for explaining the success of deep neural networks. I'm not sure I understand how much of that, but my understanding is that like see you have this broadcasting on tree model. So okay, first it is deep, yes, and it is a network, yes. The neural part, it's every like edge is has a very simple computation. So yeah, it is a deep neural network, and so it. And actually, in Alkaner's talk, he listed a number of different proposed models for statistical study of deep neural networks, and he gave like scores of these models based on a few metrics, and the conclusion one based on a few different metrics, which is roughly about deepness and about reconstruction, about explainability. Like that, and the conclusion is that yes, this broadcasting on tree model is a quite nice model for studying that problem.
Hanan Mossel was, I remember he was a graduate student of Yuval Peretz in Jerusalem, in the Hebrew University. His thesis was on reconstruction on trees. He's been working on it all his career in the, continuously.
So yeah, so this is the motivation part, and I'm spending a lot of time. And let me guess. Yeah. I'll go to the second. I'll go to the part where I'm talking about the proofs of these results, which are classical results, but I believe the proof is interesting and it sheds some light on the generalizations we'll talk about in the next part. We consider, for simplicity, we consider a deregular tree which means every node has d children. And the result is that if d times 1 minus 2 delta square is larger than 1, then reconstruction is possible. And if it's less than 1, it's equal to 1, then it is impossible. So,
but this is natural, these numbers, right? I mean, this is what you would guess if you had to guess.
yes.
Right? Because you get this 1 minus 2 delta is your correlation with them. And if you want to preserve the information, let's say you have 1 bit, you want to get 1 bit in the next level, 1 bit in the, so you want d of them. Yeah, this one is the 1 bit you are trying of information.
Yes.
You are trying to preserve as you go down.
Yes.
If you have less, then you will lose it. If you have more, then
yes. Yeah. So the intuition is that for every edge you lose information by a factor of 1 minus 2 delta square. On the other hand, as you at every level you have d times more vertices. So these are two like opposite effects, and whether reconstruction possible, it depends on whether which of these effects wins. The proof of one is by using a simple estimator. Like we use like the first definition, that is we reconstruct the root given the leaves. We consider this estimator that sigma pad of given the leaves is equal to the sine of the sum.
this is a natural belief propagation.
Yes. Okay. So so given the leaves, there is an exact algorithm to compute the posterior probability at every node, and that is belief propagation, and that is the optimal algorithm for this reconstruction tree problem. However, analyzing that algorithm is not very easy, and this is a simpler estimator. It is non-optimal, but it works above the threshold, so it's good enough for us. And in other words, another way to state this is this estimator is a majority estimator.
So if it achieves the same thresholds, in what sense is this suboptimal?
It is suboptimal in the sense that it will well, okay. So for general models, it will not work at the threshold.
But you care about like the guessing with the best possible probability rather than just beating.
Oh yeah, that is all true. Yeah, there are some cases where this gives you the not the maximum posterior. So the proof is this. So we define this Sk to be the sum. And we show that the expectation of Sk conditioned on sigma rho being plus squared divided by the variance of Sk is omega 1. And this will imply reconstruction is possible because because this quantity gives you a lower bound on the total variation distance of sigma rk considered conditioned on sigma rho being plus or minus. And that is called in information theory is called Don's covariant, but I guess in other places it has other names.
How is it called?
So Don's covariant.
Can you write it?
Okay, Don's covariant. And because of this tree structure, these two quantities are both not difficult to compute. So for the numerator, it is by linearity of expectation, and by symmetry, it is equal to d to the case power times the expectation of a single node at case level conditioned on root. And we can compute the exact marginal distribution of these two variables. So it is exactly equal to d to the case power times 1 minus 2 delta to the case power. And for the numerator, let's compute the expectation of a square of the SK. And variance is sum of expectation square times plus expected square of expectation. So we only need to show that this thing is big O of the expectation square. And again, by linearity, we can change this rewrite this into sum over leaves, sum over pairs of leaves of the correlation between sigma U and sigma V. And for each such pair, this expectation can be evaluated as 1 minus 2 delta to the distance between U and V. And now you can sum over the least common ancestor of U and V. So sum over W, and each of them, each of the W's, this is over all trees, over all nodes, and each W will contribute 2k minus distance between W and rho, and times the number of pairs that are inside the tree rooted at W. It will be upper bounded by d to the 2 of k minus dwp.
P is B.
Oh, sorry, rho.
Rho is a rho.
Rho is a root. This can be evaluated exactly, but for simplicity, I'm doing the upper bound. And finally, this thing is equal to do some algebra is d to the case power times 1 minus 2 delta to the case power squared sum times the sum of I from 0 to k of d minus I 1 minus 2 delta minus 1. And we can see that if d times 1 minus 2 delta squared is less than 1, is larger than 1, then this sum converges, and you get the desired bound. So this is a proof of the positive part, and this is this Castaner-Stegan proof, and this proof is actually quite general. It can be easily generalized to any broadcasting tree models. And as we discussed before, that is in general, if d times lambda square is larger than 1, then reconstruction is possible, and using the exactly same proof.
In this case, the channel is a binary symmetric channel, and its second eigenvalue is 1 minus 2
Yes.
And they proved it in general for any time. Kirsten and Stephen.
Yeah, Kirsten and Stephen.
Choice. You will show it?
No, I will not.
Okay.
But in general, the proof will be the same, doing the same calculation about expectation variance. Maybe yeah, let me comment that. So this result shows that in the binary case, a linear estimator is suffices, and people have considered reconstruction using and the exact belief propagation algorithm. That estimator, although it's optimal, is like quite complicated, and people have considered like simple estimators such as using low degree polynomials, and Frederick Kohler and Alexander Mossel proved some results about reconstruction using low degree polynomials, but there are still a lot of open questions. In the proof of the lower bound is more tricky. Already in Mossel's 2004 survey on reconstruction on trees, he said that at that time there are at least 4 different proofs of this lower bound, and none of them generalized to more general cases. And now 20 years later, the situation is that we have more proofs for the binary case, and very few, if any, generalized to higher up a bit. And here I'll talk about a proof I like in particular. I don't think this is like written in any of the proofs, but in any of the paper, but it's has some similarity with EKPS proof. Okay, so okay, we still have this picture here.
Is it much easier if you stay strictly less than 1? Is the equality 1? That must be the hardest, but you just want to be strict and equality becomes easier or the proof?
Yes. Yeah, I will only prove the case where the strict is 1. So here I will explain what is a belief propagation operator and do some information theory. So let's consider this picture. So if we define we define MK to be the channel from sigma rho to sigma LK.
That's not good. It's good. Nobody will believe that.
Sure. So for example, here this will be the channel will be the channel M1. However, actually in this tree, we can have more copies of L1. For example, this is also a copy of M1. And this will be a copy of M2. And this whole thing will be a copy of M3. And from this picture on the left, we have this diagram. That is, suppose we have MK. We have a box MK. Then MK plus 1 is equal to this diagram. We have copies of MK. We compose it with this binary symmetric channel. And we do a independent repeated observation of this root. So from MK plus 1, we can from MK we can get MK plus 1 by applying this operation. And this is what I call the bit propagation. And I write this as mk plus 1 is equal to bp of mk.
This is talking about the prediction or the noise, this is the noise propagation or this is the reconstruction? What you call BP is the reconstruction process or the noise propagation? You go down or you go up?
I'm considering on the level of channels. I'm considering like this this tree as a channel from the root signal to the leaf signals, and I'm saying that this sequence of channels are related by this operation.
Yeah, but I don't know why you call them belief propagation, because this is this is the introduction of noise that occurs in reconstruction.
Okay, yeah.
So,
If you I would say that these channels they will be represented by distributions on the interval, and to compute this BP operator, you will actually do this reverse process about inference, and that is the BP propagation part. So the plan is this. So suppose we have a channel P, and we want move C of okay.
let me ask you a question today. Is the word channel okay for everybody?
Okay, sorry, if you don't like the word channel, then it's the same thing as a Markov kernel. Or some probability kernel. Basically, it's like a process that given an input, it will produce a random output. We'll prove that the BP operator, it contracts information. That is, for certain information measure C, we'll prove that this C of BP of P is upper bounded by D times 1 minus 2 delta square of C of P. And if this holds, then we can we observe that the reconstruction problem is about a limit of k goes to infinity of the say some information measure might be neutron formation, but root and the leaves. And this thing is will be upper bounded by or this information measure C of this channel. This is BP applied case to the identity channel, and it will be upper bounded by the limit of D times 1 minus 2 delta squared to the case power of this C of identity channel. And the C of identity channel, it should be something constant. So if D times 1 minus 2 delta squared is less than 1, then this limit will go to 0.
And there is an inequality also in the second line, right?
Well, it depends on the it depends on what is my definition of C and I. But actually, in here we can just take C to be okay. So this channel P is from X to Y. Then we can see of P is can just take it to be the mutual formation between X and Y. So in this case, this is equality. So our goal is to prove that C of BP of P is upper bounded by D times 1 minus 2 delta squared times C of P. And this inequality is like very familiar to information theorists, and it can be like proved without thinking for them. And so that for this we need like two primitives. So in the BP operator, we first pre-compose it to the BSC channel, and then we take independent observations, and we can decompose it into the two-step process. We can okay, yes. We first from P we go to P pre-compose with BSC. And then from this channel, we go to these independent observations. This is step 1, this is step 2. In step 1, the result is that C of P pre-compose with BSC delta is upper bounded by 1 minus 2 delta squared of times C of P. And in the second step, show that if we have like D independent observations of Q, then this whole channel, the capacity is upper bounded by D times C of Q.
C is not capacity. I mean, C we defined it to be inside.
Yeah, it's defined to be the mutual information between these two variables. And here I'm taking this x variable will be a uniform 1/2, and P will be a certain kind of symmetric channel. So this thing is equal to the capacity. Yeah, that is why I denote this information measure using C.
I have a question.
Yes.
In these two steps, is it possible to find out like what is the remainder term and then therefore like talk about the equality case when the two delta squared is equal to 1?
Yes, I think that is possible. And so in the equality, okay. Yeah, so for this inequalities to be equality, this channel P need to be satisfy some special properties, and importantly, they cannot be. I think only the trivial channel satisfy equality here. Therefore, for any non-trivial channel, if you apply the BP operator, you have strict equality.
Also, does this proof generalize to the general tree case with the branching number?
Sorry, general tree with branching number?
Yeah.
Yeah, it is generalized to a branching number. But to do that, I need to define branching number, which is kind of flow, and but that you can define a flow from this process. So let me talk about the proof of these two primitives. And the first one, okay, I would say both of these are like familiar to information theories. But the first one is what we call strong data processing inequality. So in data processing equality is an equality which says that if you have a Markov chain U to X to Y, then the mutual information between U and Y is upper bounded by the mutual information between X and Y. And here we have we are strong DPI means that this inequality actually holds with some coefficient. And in our case, we'll take the channel from U to X to be BLC delta, and the channel from X to Y to be P. So this statement 1 is equivalent to saying that strong data processing inequality holds with eta equals 1 minus 2 delta squared. I plan to talk about the proof of this inequality, but sure. I guess I'll talk about it nonetheless. So why this is not a difficult thing to prove? At least in our case, our P, like we'll take our P, for example, to be the channel from sigma rho to sigma LK. And it will be it will satisfy a property that satisfy a symmetric property, and this property will help us decompose this channel into easier pieces, and in a way that makes this SDPI easy to prove.
P itself was M1, will it be totally clear?
Sorry?
If P was M1, not MK, but M1, will it be really easy?
I want to like I want to be an explicit case, or I want to show that like there are the general definition, that like a definition that we want to make that will make this proving this inequality easier. This is information theory called binary memoryless symmetric channels. And abbreviated as BMS. And this memoryless part is from some considerations in information theory about channels that with feedback, but we can ignore that. And the important thing is that it's binary, it has binary input, and it is symmetric. In what sense is symmetric? So we have this channel P, it is from some inputs, from input plus minus to some output space Y. And we can partition this Y into Y plus union Y minus. And there is a bijection between these two sets. So consider that consider our channel sigma rho to sigma LK. If you flip the input and flip the output, the transition probability will stay the same. So the definition of the BMS channel is that your transition probability from plus to some output alpha bit is equal to the transition probability from minus input to minus Y. And the useful property here is that every BMS channel X BMS channel is equal to a mixture of BSC channels. What does this mean? You can consider this y plus and y minus as parameter as parameter deltas. So so our P channel is equivalent to a channel that goes from X to delta of Y, where delta is from some distribution 0 to 1/2, and Y is BSC delta applied to X. This says that you can partition the output alphabet Y such that on each part of the partition you have a little piece of BSC channel. And why is this useful? So let's call this let's call this delta P, where it is a random variable from on the interval from 0 to 1/2, and this is some random variable that you related to the channel P and actually uniquely determined by channel P.
Sorry, have you defined BSC delta?
Oh, I'm so sorry. I should have defined this in the very beginning. So BSC delta is a channel from a plus minus to plus minus, where BSC delta of Y given X is equal to Y minus delta if X equal to Y, and equals delta if X is not equal to Y. So it is the broadcasting channel on every edge of the broadcasting trees.
Probability 1 minus 2 delta, you keep the bit you have, with probability 2 delta, you flip a third one.
Yeah. So here you mean by mixture of BSC, you mean you have what do you mean by mixture? Like
yes. Let me find some place. Sure. By mixture, I mean this. So suppose we have a collection of panels. Let's say C, and it is okay. Here we are taking it to be the class of BSCs. They have the input plus minus to output plus minus, and we denote this as Y delta. This set as Y delta. Like
Okay.
they are.
I guess intuitively, you simply first pick what is the noise level
Yes.
using some distribution, and then for the delta, then you don't have a fixed delta in advance, but you have a distribution on the noise level delta.
You're also picking the output alphabet.
No, the output alphabet is
But if the output alphabet is plus minus, isn't this just
No, I think it's a
yeah,
general.
you're right. You need a large
that's what I'm confused about. Like what's
Yeah. So your mixture channel has input alphabet plus minus, and the output alphabet is the disjoint union of all the Y deltas. And your channel maps input X to your first decide which data you are use, and then you decide the output. And an example is so suppose we consider erasure channel. This is a channel from plus minus to plus minus and star that maps S go to X with probability, let's say just 1 minus epsilon. This goes to minus X with probability 0. With go to star with probability epsilon. This channel will be equal using okay. So first, this channel is a BMS channel because you can take your map to plus to minus, minus to plus, and star to star, and so it's a BMS channel, and it has a BIC mixture decomposition, and this in this notation it is equal to let's say 1 minus epsilon times BIC 0 plus epsilon times BIC 1/2, which says that with probability 1 minus epsilon, you observe through the BIC 0 channel, which is you observe exactly your input. And with probability epsilon, you observe through BIC 1/2 channel, which is your forget your input.
You also like observe which of the two cases.
Yes. The data is also part of the observation.
Another example would be just two levels of the tree, right? You have this four outputs, 0, 0, 0, 1, 1, or everything, plus, minus, right? And you can decompose them. The two middle ones, you have one with probability delta, one probability 1 minus. These two are really 1/2, and they happen with probability again. With some probability you go in the middle two, and some probability you go in the outer two. In the middle two, well, okay, sorry. Anyway, but that's a good exercise anyway. So I think a good example to decompose this two channels. To make sure the channel is very simple.
So this general fact here, like this Y alphabet is allowed to be just any set. I guess negative Y needs to have a meaning, right?
Yeah, okay. So the technical definition is that there exists an involution on the set Y, and the negative Y will be applying that involution. But in most cases, the involution will be obvious, so we do not state that. So why the BIC mixture is useful because it gives you a easy it gives you a easy formula for the capacity of the original channel. So actually we have a capacity of P is equal to its expectation of capacity of BIC delta P, where delta P is this data component in the BIC mixture. Also, the capacity actually okay. The composed channel P P composed with BIC little delta. Its delta component will be okay. Let's see, log of the delta of decomposed with BIC delta. It is the expectation of delta P at the expectation of the single point measure at 1 minus 2 delta times large delta. So this line means that from the BIC decomposition of P, we can easily write down the BIC decomposition of P composed with BSC delta. But I can erase. So from the above two lines, we see that the capacity of P composed with BSC little delta is equal to expectation over delta P of the capacity of BSC delta P composed with BSC little delta. Actually, yeah, BSC. Sorry, this is not exactly correct. There should be something like this, but it's a simple formula using little delta and capital delta. So we have formula for capacity of P and capacity of P composed with BSC delta, and our goal is to prove this SDPI, and so we now have reduced this SDPI to BSCs. Because this both are taking expectations over the data parameter of P, and here we have capacity of BSC capital delta, and here we have BSC of capital delta composed with BSC little delta. So we reduce the original, we reduce the thing we want to prove to thing about BSC channels, and so now we only have like two real parameters, and this can be proved directly.
But you need convexity.
No, we don't need convexity because here the expectation is on the outside.
Oh, okay.
And so this is how we use the symmetry property of the BMS channels to prove this SDPI. And the second part is almost the same as we can use we use BSC mixture to reduce to BSCs. The next explicitly calculate.
You can't just use some kind of general for the mutual information.
Yes, yeah, that's the either way for information series. Because so simple was saying that there is a sub-activity of mutual information that says that whenever you have things like x, y, z, then mutual information between x and y, z is upper bounded by mutual information between x, y, plus mutual information between x and z. And yes, this is like another way to prove this. So this so using this BMS mixture decompositions, we have proved these two inequalities, and these two combined will give us this inequality, and so here these steps will follow. and we have proved the non-impossibility of reconstruction. And yeah. Are there more questions about the proof? Yes.
Are there other problems where you can use this to establish like non-uniqueness of the Gibbs measure?
Uniqueness is like a different question. Uniqueness is not about information channels. So you cannot really use like this those data processing inequalities, these kind of things to do that. But you will have similar kind of contraction and additive phenomenon that is like in some sense they are high level is they are similar, but on the end they are different proofs.
And is there any analogy of this mixture property for non-binary alphabet? Or
Yes.
Yeah.
So for if you consider the coloring model, so you have a Q-array alphabet, and then you will instead of decomposing to orbits of size 2, you will decompose into orbits of size Q factorial. That is so your generation of these BSC channels will be like channels indexed by probability distributions on Q alphabets. And you can so you have a similar decomposition there. You can decompose a complicated channel into Q parameters.
If the symmetry group is acting on your channel, then you can.
Yes. Yeah, and if the symmetry group is not a full symmetry group, you can have some weirder things in the same spirit. Yes.
What if your alphabet is like, let's say R or 0 through 1, like not discrete?
Okay, so yeah, so in that case, I guess you can't really do this kind of decomposition, but you still have like you still have versions of this strong data processing inequality and subactivity. So it is you will not prove using this decomposition, but but using certain inequalities that work for continuous alphabet, you may get results like this. Actually, in one of my papers, I considered a broadcasting tree version where instead of plus or minus 1 alphabet, your alphabet is on the unit circle, and your noise is adding a Gaussian noise. And in that case, we actually have exactly the same inequality. It holds at the lambda square, where lambda is the second larger eigenvalue.
So why wouldn't this prove that reconstruction is impossible below the KS threshold?
Sorry, good question.
Why wouldn't this prove that reconstruction is impossible below KS?
Okay, so this will prove that the limit mutual information goes to 0. Is that part okay? Yeah, and this, because your sigma rho has full support, this goes to this mutual information will be within a constant factor of the total variation between sigma Rk given plus and sigma Rk given minus. And if this goes to 0,
I guess I was seeing like why would this work for like larger alphabets? I thought for larger alphabets the KS threshold is not the same thing as.
Yeah, so for larger alphabets, the KS threshold is no longer the reconstruction threshold. Depending on what information measure you use. If you still use mutual information, then this contraction part will fail. But the subactivity holds. And if you use chi-square information, then the contraction part will be good, but the subactivity fails. And we know that because they are not the same threshold, so it's good that they fail. And yeah, I would like to discuss one like hypertree case where the same thing that the KS threshold fails. I would like to say that Alkan Mosso and Alan Sly and other people have studied a lot about the Q-array case of this broadcasting tree model, where it's called the POS model, and they have found very interesting phase transition phenomena in that case. But I will not discuss those today, and instead I'll discuss a generation in the other direction that is considered hypertree.
I obviously to give my info on the first floor here.
In the hypertree case, instead of edges, you have hyper edges. In here, we have hyper edge of size 3. And still, the root has a uniform plus minus. And for each this hyper edge, the parent is U and the children are V1 to V2, VR minus 1. And R is the hyper edge size. So there are R minus 1 children. So here the children will be equal to will be all equal to sigma U with probability. With probability lambda plus 1 minus 2 lambda over 2 R minus 1, and it will be anything else with probability 1 minus 2 lambda to over 2 to R minus 1.
This is a strict generalization of the case of edges.
Yes, yes. So in so in this case, R is equal to 2 and lambda is equal to 1 minus 2 delta. Yeah, I tried to use lambda because it is the second largest eigenvalue and easier to work with. And we can define the reconstruction problem similarly. This 3. And now I can state our result. Okay, the first one actually I'll not say that's our result. It's like it is a Castan-Stegan threshold, and it is like well known. So the first part says that if r minus 1 times d times lambda square is larger than 1, then reconstruction is possible. And the second part, as I hinted before, this will not be the same as the tree case where you have less than or equal to 1, then reconstruction is impossible. Instead, we have this. So it has some complicated phase transitions depending on the parameters. So Ks is a Castan-Stegan, BOHT is short for broadcasting on hypertrees. And a result says that for if R is equal to 0 or 4 and lambda is larger than 0, then the Ks is always tight. Or if lambda is here for small d, actually I mean when lambda is larger than 1/5, then Ks is tight. And in the case where d is large, we prove that when R is larger than 7, larger or equal to 7, Ks is not tight. But when it is at most 6, then Ks is tight. So if you are like let's say for the QRA case, like for the post-model case, you get something similar but not entirely the same. And here you have so there you also have like different tightness for large d and small d. But I find this like very interesting. And yes, all these results are in these two joint works with my advisor, Yuri Polyansky, and a graduate student, Aridia Pandey at Princeton.
So can you it's really interesting and very weird, but can you have can one guess, or is there some intuitive reason what happens for these parameters where you don't, in general, when the Castan-Stegan doesn't, is not the right answer. What happened? What other phenomena comes in that makes this expectation analysis fail?
Yes.
The Castan-Stegan is the expectation analysis of belief propagation.
Yeah. So the short answer is that the Castan-Stegan bound is about the first order behavior of the of certain information measures on the belief propagation recursion. And so there are and it's so in general we shouldn't expect that the first order behavior will also hold in general. So let's
what's the simplest example of this? Maybe in a different statistical model is a very simple example where the first order this related to first order, second order phase transition also.
I'm not sure about that, but let me write down a few things so that so let's consider another information measure which I will not define. It is another information measure, and then PS is saying that C square of BP of P is equal to d lambda square of r minus 1 d lambda square times c square of BP of c square of P plus lower orders. Therefore, if your c square of P is small enough and you are below the Castan-Stegan, then you will expect the limit goes to 0. However, this is only the first order, so in general, it might happen that it does not contract.
You say the KS threshold is not tight, that means like you have a better reconstruction.
Yes. And yeah, I can talk very briefly about the proof. So there are like two like okay, it's here a bunch of different results, but these are mainly in two parts. And the first is when D is not too large, but let's see R equals 3 and 4, lambda larger than U0 and general R, and lambda larger than 1/5. And the second part is about large D for R equals at most 6 and R at least 7. For part A, our proof will be the strong data processing equality plus subactivity that we have seen for the binary case. Here we still have the channel from MK to sigma rho to sigma LK, and nicely they are still binary memberless symmetric channels. But the BP operator is slightly different. So starting from MK, we will first compose with these triangular channels, and then we will join a few copies together. So in here, for the contraction subactivity method, we want to prove two things. The first one is that we want to prove that the capacity of this composed with the triangular channel is upper bounded by R minus 1 times lambda square times the channel P. And the second is that capacity of this independent observations is upper bounded by D times the capacity of Q.
These are the cases where it's this you're talking about. A is the case where the second bounded stack.
Not exactly, because in part B, when R is at most 6, Casson theorem is also tight.
But anyway, this is the case
Yes.
where it's the same. The bounded
Yes. Yeah. And as Xinhao said, that the second part is always holds for mutual information. So so this is good. But it turns out that the first one is always false for mutual information. So so what do? The mutual information doesn't contrast very well, as this framework is like robust, and we only want to find some information measure such as this two will hold. And And for one thing we could use is what's called chi-square capacity. And this is expectation of 1 minus 2 delta squared under the BIC decomposition. And for this one, it will give you the result for lambda at least 1/5, and the result for r equals 3, lambda larger than 0. Okay, and there's another case in 2A that is for r equals 4. And for this, we actually need to use another information measure that is called symmetric neutron formation. Symmetric KR divergence. Symmetric KR information. And you're using this DSKR. And this give you the definition. It's equal to expectation of half minus delta times log of 1 minus delta over delta. And for this one, using this one, we can get the result for r equals 3 and 4 and lambda larger than 0. So it is like interesting that using different information measures that we can get different tightness of different lower bounds, but and each is better in their own regime. And I need to comment on this r equals 4 part. That is so by using the BIC decomposition, to prove this contraction inequalities, we need to prove an inequality in a small constant number of real parameters, as like with 3 or 4 parameters, and this inequality is like it's easy to numerically verify, but giving an analytic proof is not so easy. And in our preliminary version of the paper, we stated that we verify this numerically, but we put this as a conjecture. And later, Kuna Mawaha helped us prove the inequality for r equals 4 case.
Sorry, can you remind me what the delta P means?
Yes. So a BMS channel P will be same thing as the BIC mixture, where the parameter is BIC delta, and this delta P will be a random variable that's supported on 0 to 5.
Thanks.
So this is about proof of the first part, and the second part is using large degree asymptotics. Plus Taylor expansion, or we want to call it robust reconstruction. And I usually call it slice method because it is developed and major part is developed by Alan Slice during his research on Potts models. So he studied the carrier model in 2009 and the pulse model in 2011, and he proved tightness about cascade theorem for the pulse model when Q is at most 3 or at least 5. And the method, his method is further improved by Mosso-Sasson in last year, and they determine tightness of KS for Q equals 4. Actually, okay, I can write on this board. So the Taylor expansion part is actually this line I wrote here. That is when C chi-square of P and when this chi-square information of P is very small, we have this expansion, and so we know that at least when this is less than 1, then this will go to 0. However, to actually use this, we need one more order, which is as follows. This is the main expansion in the robust reconstruction part, which says that if r minus 1 times d lambda square is less than or equal to 1, then there exists then for small enough C chi-square of P, this thing will contract. It's not very obvious, but you believe me that this coefficient for the second degree is negative. And the important thing here is that this smallness of C chi-square of P does not depend on your choice of d and lambda. Means that there exists lambda such that for all C chi-square of P less than lambda and all r minus 1 d lambda square less than 1. That's this thing holds. So importantly, this epsilon does not depend on the choice of d and lambda. And so proving this is quite a computation. Like we have like for this particular result, we have like 18 expansions that we need to do, and the hardest of them has 21 terms. But in the end, RDF and I are able to, and at some point we use computer assistance, but in the end we are RDF and I are able to perform this computation all by hand. And so this is the robust reconstruction part, and the large degree asymptotics part. This is I'll say this whole method is developed by Sai, and his intuition comes from the mean field models, the analysis of mean field models, where you have a very large degree, and so you can use Gaussian variables to approximate your influence. And this part is the part where we need to use the large D assumption. If D is very large, then lambda is very close to 0. And in the BP operator, we have this independent observation part, and previously we found it using subactivity. However, this part is very non-tight. It's not tight and can be improved. The reason is that here d is very large and lambda is small, so it can be approximated by a function that it can be approximated by a function which involves certain Gaussian variables. And if we perform this approximation, we'll get that the chi-square capacity of BP of P is approximately, let's say, G of C chi-square of P, where G of X is expectation over a Gaussian variable, and of S plus square root of S times Z, where S is equal to d lambda square over 2 times 1 plus X to like at 1 plus to r minus 1's power minus 1 minus X to the r minus 1's power. So it's some explicit function involving Gaussian variables. And if this G has no fixed point, then we can show that as you iterate the BP operator, the limit will go arbitrarily small, and then you will apply robust reconstruct to conclude that Ks is tight. On the other hand, if G has a non-zero fixed point, then we can show that as you apply the BP operator, the chi-square capacity of your channel will always be lower bounded by that fixed point. And here is the plot for Gx minus X. For r equals 6, you get something like this. For r equals 7, you get this. So at least numerically, we can observe that for r equals 6, this G function has no fixed point except for 0, and r equals 7, it has a no true fixed point. And by doing some numerical by doing some rigorous numerical computations, we are able to prove the fixed points properties of these functions. And in this way, we prove the results for large D. So let me do a quick summary. That's we are seeing that for this reconstruction on trees and hypertrees problem, the casting theorem bound gives you an easy upper bound, and it always works. However, for the lower bound, there are like a variety of different methods. We talk about two methods. One is based on contraction and subactivity, and the other is based on large degree of asymptotics. And when the first method does not work, it's interesting open question to see how we can prove any non-asymptotics results about this problem. Thank you very much. This is my
Questions?
But does this have any implications for sampling off hypergraph, say, or the other like applications you mentioned before?
Yeah, so this reconstruction on trees, so okay, immediately they give this will imply bounds on weak recovery for the statistical model or hypergraph versions of the statistical model. And that also implies bounds on the condensation threshold for in particular for the not all equal set. Means it's a variation of set where for each clause you have a set of variables and you don't want them to be all the same. And also for the QR version, and also for the hypergraph by coloring. And if you consider the QR version, the post model, then it will have implication on the condensation threshold for the random coloring model. But in that case, I guess is you have better bounds using other methods. But now, okay, that's about condensation threshold. And also I discussed that the conjecture that the clustering threshold is the reconstruction threshold. So it is meaningful to compute this threshold.
Yeah, so some of the average case problem are hard at the more dense regime where it's not like you have bounded D degree. In those kind of cases, there is something analogous to tree reconstruction.
I think my understanding is that when you have when your degree is larger, then the problem somewhat it becomes easier because you can use this Gaussian approximation freely. And I think for example for statistical models, for when the case where D is large, you have very tight calculations.
Maybe you mean computational? Is that what you mean?
Yeah, I think I was thinking about even I was thinking about things like planet clique where instead of D being a bounded constant, it actually depends on the number of vertices in your entire graph.
Yeah. So I think I want to say is that when D is larger, then this Gaussian approximation is more likely to work. And when it works, you get analysis of Gaussian functions. And so
in this large D regime, you have a full state evolution description of the evolution of BP.
Yeah, the statement here is that for any for any delta there exists D0 such that for all D larger than 0, this thing is within G plus minus delta. So we have some quite not too bad. First, we have some control about the evolution of this classical characteristic. And if you care about the actual distribution, then it will be something related to Gaussian, I believe. Yes.
I've actually commented this. You gave a very large number of motivations to study this. It's also in computational complexity. People study things like this. I don't know how many people here know that the majority function on NBX has a polynomial size formula. This is a non-trivial result, and it was first discovered by Valiant, who said a random formula of polynomial size will compute majority. The formula is take a binary n-door tree of depth 5.3 log n. And for every, you have n variables. For every leaf, put a random variable, one of your random variables. This formula with probability 1 will compute the majority on this distribution. It's not hard to prove that, and it's actually a sort of reconstruction, if you think about it, or analysis of the same nature of the reconstruction things. It was later, I mean, there's, people who know about isochromous the AKS network for sorting. It also solves it, but it's a formula not of size n to the 5.3, but n to the 1,000 or million or something, whatever. But the question of how tight is this 5.3 or what's the smallest formula for the majority function? People use things of this nature to put that this sum up, it's really an amplification result, variant formula. So I don't want to talk too much, but people use arguments of this nature to prove that some kind of formulas will actually need n to the 5.3. And this is the information theory or reconstruction bounds basically on amplification. So anyway, just want to mention, if you didn't know about it, you should find out and you should prove for yourself that majority functions have the size formula.
Sort of get a subgroup. Yeah.
Any more?
When Lars and all that.
All right, thanks.